You know that feeling when a car takes off and you get pushed back into your seat? Or have you ever looked up at the night sky and wondered how a satellite just stays up there? Well, it's not magic. It turns out there's a kind of secret code that runs the entire universe of motion. And in this explainer, we're going to crack that code together.
So, let's just jump right in with a classic question, one you've probably wondered about yourself. You're on a roller coaster, you're going into a loop, and suddenly you're upside down, hurtling through the air. So why don't you fall out? What is keeping you in that seat? I promise, by the time we're done here, you'll know exactly what's going on. That feeling of being pinned to your seat, that's the key to everything. It's the heart of a whole field of physics called dynamics. And dynamics is all about asking the most interesting question, not just how things move, but why they move in the first place. Now, this is a really important distinction to make. You might have heard of kinematics before. That's like the sports announcer just giving you the play-by-play. How fast the ball is going, how far it went. It just describes what happened. But dynamics is the coach in the locker room explaining the strategy. It's about the forces, the pushes and pulls that cause the ball to fly through the air. It's the why behind the what.
So how do we get to that why? How do we explain all these forces? Well, lucky for us, a genius named Isaac Newton basically handed us the Rosetta Stone for motion centuries ago. These aren't just some dusty old rules in a textbook. They are the fundamental code that runs everything.
And here's the code, right here. First up, the law of inertia. Basically, objects are kind of lazy. They just want to keep doing whatever they're already doing. Second, and this is the big one, the force equation. If you want to change an object's motion, you've got to give it a push or a pull. Simple as that. And third, action-reaction. You literally can't touch anything without it touching you right back. These three simple ideas, I'm not exaggerating, they explain pretty much all motion.
Okay, so knowing the rules is one thing, but actually using them to solve problems, that's where we need a game plan. We need a way to see all these invisible forces at play, and that game plan, that blueprint, is something called a free body diagram. It is, without a doubt, the most important tool you have for this.
And I really cannot stress this enough. This might be the most important takeaway of this whole explainer. Your free body diagram, or FBD, has to be your best friend. If you get this map of forces right, the rest is just math. But if you get it wrong, you're basically lost in the woods from the very beginning. It's that critical.
So what kinds of things go on this blueprint? Well, we've got a few usual suspects that show up all the time. You've got gravity, of course, always pulling straight down. Then there's the normal force, which is just a fancy way of saying the surface is pushing back. You've got friction, which always tries to stop things from moving. And then you might have an applied force, like a push or a pull from something.
All right, enough talk. Let's actually put this into practice. Let's solve a real problem. We've got a box, someone's pushing it, and the floor is creating some friction. The question is, how fast does it speed up? To figure this out, we're going to need our blueprint, our FBD, and Newton's second law.
Okay, so the first thing, the most important thing, is to find the net force. Think of it like a tug of war. We have 20 newtons of force pushing forward, but friction is fighting back with 5 newtons. So the box only really feels a net push of 15 newtons. Then we just plug that into our big formula, F equals ma, do a tiny bit of rearranging, and boom, we get our answer. The box accelerates at 3 meters per second squared. See, the blueprint makes it easy.
So, a box on a flat floor, that's a good start. But let's be honest, the real world is way more interesting. It's got hills, ramps, curves, and yeah, roller coaster loops. And the beautiful thing about Newton's code is that it works for all of that too. You just have to know how to apply it. Here's a pro tip for any problem that involves a slope or a ramp. See, gravity always pulls straight down, which is kind of awkward when your ramp is at an angle. So here's the trick. We do a little bit of geometric jujitsu. We split that one gravity arrow into 2 smaller, more useful parts. One that pulls the box down the ramp and another that pushes it into the ramp. By just changing our perspective like this, the problem becomes 1,000 times easier.
And that brings us all the way back to the beginning, our roller coaster. The secret to anything moving in a circle, whether it's a satellite or you in that loop-de-loop, comes down to this single relationship right here. Now, this isn't some new magical force. Think of it more like a requirement. It's the price of admission you have to pay to travel in a circle.
Okay, listen up, because this is the single biggest point of confusion for so many people. Centripetal force is not a thing, it's a job description. It's the net amount of force that's already there pulling the object toward the center. So at the very top of that roller coaster loop, what forces are pulling you down toward the center of the loop? Well, gravity is, and the track itself is also pushing you down. So gravity and the normal force from the track team up to provide the exact amount of net force you need to stay in that circle. And that, right there, is why you don't fall out.
You know, once you really understand this code, you're going to start seeing it everywhere. It's like putting on a new pair of glasses. It's not just stuff for a physics class. It's the invisible architect behind so much of the world around us.
Think about it. When a car slams on its brakes, your body wants to keep going forward. That's inertia. And your seatbelt is what provides the force to stop you. Those banked curves you see on the highway, they're designed to help provide the centripetal force your car needs to make the turn. And satellites, they are literally in a constant state of falling toward Earth, but they're also moving sideways so fast that they just keep missing it. Gravity is providing the centripetal force that bends their path into a perfect orbit. It's amazing. So let's just take a quick look back at what we've accomplished. We cracked Newton's three-part code. We learned how to draw the most essential tool, the blueprint of a free body diagram, and we used those tools to figure out everything from sliding down ramps to surviving a roller coaster loop. You now have the fundamental toolkit to see the why behind all motion.
But here's the thing. As powerful as forces are, this isn't even the whole story. There are even deeper, more fundamental ideas that govern the universe, energy and momentum. And that's exactly what we're diving into next time. You are not going to want to miss it.
Hey, if this explainer helped you crack the code of motion and maybe see the world in a slightly different way, do me a huge favor and hit that like button. It really helps. And make sure you subscribe so you don't miss our next deep dive into the physics that shapes our world. Thanks so much for watching.